Okay, so tangent line. We're trying to approximate this, or calculate actually, the slope of the tangent line, which is something, right? I mean, that is a positive slope. There is a value to that line. And we do it by finding the slope of a secant line. Now, you dealt with secant lines too in geometry. If you remember all those, here's a circle, and you would have to say, what is these are two secant lines. What is the measure of this angle? What is the intercepted arc? Do you remember all that kind of stuff? I mean, these lines were called secant lines. That's what these are here. Because now this line is actually crossing the graph in two places. Tangent line, one place. Secant line, two places. Right? And the 2 points are f of x. Okay, whatever is the x value, then the y value is f of that value. And this point here is the x value is x plus h, where h is some number that we're adding to the x, right? And it's far apart, farther apart here than it is on these. And so the function value would be f of x plus h. So what they're trying to show in this series here is first the h is bigger, and then it gets smaller, and the slope of the line gets closer to the slope of the tangent line. And then the h gets smaller, and the slope of the line is closer to the graph of the tangent line. And we'd like to let that h get as small as possible. But can we ever let those 2 points come together? Can we ever calculate the slope if you actually only have 1 point? You know, if you use the same point in the y2, y1, x2, x1, you're going to get 0 over 0, right? So this thing would not have a value if we actually let the points come together. But we know it has a value, right? We know from there it does have a value. So that's the tangent line problem. And there was one part of the last section that we didn't actually already do, and that was evaluating for a particular function the limit of a difference quotient. Right. We did difference quotients back in chapter 1. It was the first section that we did, which was 1.4. Now the thing that's different now is we are going to take the limit of it. Right. We couldn't do that back then because we didn't know what a limit was. Well, let's see. First of all, if I looked at this limit of a difference quotient, what would I get if I did a direct substitution? If I plugged in the h equals 0, what would that fraction equal? I mean, this become f of 3 plus 0, which is f of 3. So the numerator would be f of 3 minus f of 3, which is 0, and the denominator would be 0. We'd have an indeterminate form, right? So let's try to simplify what we can simplify here. If this is the f of x squared minus 1, how do you find f of 3 plus h? Right, if that's f of x, how do you find f of 3 plus h? You plug in 3 plus h right there, right? So this is 3 plus h squared minus 1, right? And we need to simplify that. And I'm going to do this 9 plus 6h plus h squared minus 1. I just FOILed the 3 plus h times 3 plus h. Okay, now I'm going to subtract the f of 3. Okay, what is f of 3? Right, plug into this function here. Right, that's going to be 3 squared minus 1 equals 8. Well, let me do this before I take that step. I shouldn't have gone ahead. Before we go ahead and do that part, let's combine the like terms in this one, right? That was 9 minus 1, which is 8, plus 6h minus h squared. And now we'll do our f of 3, which is 8. What's that? Where? Oh, yeah, you're right. Plus h squared. Okay, so now in the numerator of this difference quotient, we've got f of 3 plus h minus f of 3. So just go ahead and do that. right? This is f of 3 plus h minus f of 3 equals, and the 8's cancel, right? And all that's left is 6h plus h squared. And now because this, right, it's divided by h, so I divide both sides by h. And what should happen is, whenever you do the numerator, you should lose every term that doesn't have an h in it. So everything that's left in the numerator has an h in it. You're going to be able to cancel the h in the denominator, right? This thing is 6 plus h. So actually, this limit right here is the limit as h approaches 0 of 6 plus h. Okay, now do direct substitution. What do you get? 6. So the limit is 6. So we started with a indeterminate form, and we just go ahead and simplify the difference quotient, and then we took the limit of what was left, and we got 6. Okay, we good. Good. So the definition of the slope of a graph is just what we did right there, right? The m equals the limit of the slope of the secant line, right, as the h approaches 0. And you could write it like this. The limit as h approaches 0 of f of x plus h minus f of x divided by h, provided that the limit exists. So what we just did, right, that is slope. I think I got something written down here I need to look at. Right, so we can use this for any kind of function. You know, could be linear, could be nonlinear. You know, but do we need to have this kind of a definition of the slope to find the slope of a linear function? No, we don't. We know the slope of a linear function, right? It's a constant that we can tell just by looking at the equation, right? That's mx plus b. So what's the slope? Negative 2. Is it the same slope for every value of x? Yes, it is. It's the same thing. So let's go through this slope process, even with a linear, just to show how negative 2 is a constant slope of this function. Okay, so we're going to be doing the limit of the difference quotient. So the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay, we need to know the f of x plus h. And what is that? Right, I'm going to take the x plus h, I'm going to put it in there. So that's negative 2 times x plus h plus 4, which is negative 2x minus 2h plus 4. Okay, now we need to subtract f of x, right? Because that's what it says to do. So f of x is this, negative 2x plus 4. Like I said, when you do this subtraction, it should be that every term that doesn't have an h in it cancels. Right? So f of x plus h minus f of x equals, and the negative 2x's cancel and the 4's cancel. So all that's left is negative 2h. And then because this has a divide by h in it, then you got to divide by h. And again, since every term in the numerator has got an h in it, it'll cancel the h in the denominator. This is negative 2. So we're not done yet, right? Now we're going to go back here and say the limit as h approaches 0 of negative 2. Right? And that was one of our properties of limits. Right? What is the limit of a constant, or the limit of a constant function? It's the constant, right? I mean, this is like saying this is that function. It's not the number 2, negative 2. It's the function f of x equals negative 2. It's a horizontal line. Every y value is negative 2. So what is going to be the limit as h approaches anything? I mean, negative 2. So we kind of already knew that, because straight lines, we can tell the slope just by looking at it. But it actually works its way out here too. Actually, I did these two examples in reverse order. I didn't do number 3. We're going to go back and do number 3 now. Right. Number 3 is x squared. It's a quadratic, and it's actually at the point negative 2. Okay. Now I think I've got this on here twice. I do. So if I'm going to do this like we've already seen them do this, this is the way that it works, right? We're going to say the limit as h approaches 0 of f of negative 2 plus h minus f of negative 2 divided by h. But we're putting in, we know where we're trying to find it. We're trying to find it at negative 2. So that's why I plugged in negative 2 here and here. So what is f of negative 2 plus h? Right, plug in this, there. So that is negative 2 plus h squared, which is 4 minus 4h plus h squared. Right, now, f of negative 2 equals what? Negative 2 squared, which is 4. Subtract. Okay, again, it's canceling the only term that didn't have an h in it. Right? If you get to that point, you're not doing that, then you did something wrong. So this is f of negative 2 plus h minus f of negative 2 equals 4's cancel, negative 4h plus h squared. Then what am I going to do? Sure. I got to divide by h, right? I've only done the numerator. Now I got to do the denominator. Divide by h. Divide by h. And again, because every term in the numerator has got an h in it, you can cancel the h in the denominator. This is negative 4 plus h. So we are taking the limit as h approaches 0 of negative 4 plus h. Okay, so what method do you use now? Direct substitution. Now just try to plug it in. If it's defined, then you're good, right? So right there, negative 4. So slope is negative 4. Now we're going to do the same problem, but this time we're not going to use x equals negative 2. We're just going to say, we're going to calculate the difference quotient of x plus f of x plus h minus f of x, right? That's going to give us a formula for the slope for any value of x, and then we'll plug in x equals negative 2. Okay, that'll look like this, right? the limit as h approaches 0 of f of x plus h minus f of x divided by h. Right? The f of x plus h will be x plus h squared, which is x squared plus 2xh plus h squared. Right? Minus f of x f of x plus h minus f of x equals, and the x squareds cancel. And now what's left? 2xh plus h squared. Right? Divide by h equals 2x plus h. Right? So the limit as h approaches 0 of 2x plus h, right? You do direct substitution and you get 2x. Right? So this is actually a formula for the slope. I mean, the slope of the graph of a quadratic, because it's a curved line, it's changing all the time. It will be different depending on the x value that you plug in. If you want to know what the slope is at this point, right, then you plug in the x values. The y value doesn't matter. Plug in the x value, right? At negative 2, 4, 2 times negative 2 equals negative 4. Now, when you calculate the slope and you don't have an x value plugged in already, you're going to get a formula for the slope, right? And now that formula has got a name. Let's wait for everybody on that. Okay. That formula's got a name. It's called the derivative. And if you look at this definition for a derivative, it's exactly the definition we used for a slope before. Okay. And you spend about the first half of the first calculus class you take finding derivatives. Right? What is a derivative? Derivative is a slope. Right? What does the slope represent on a graph? It represents the rate of change. Right? If I've got a function that describes how pressure is changing with time, right? The derivative is telling me how if I've got a function that describes the pressure at any point in time, the derivative is telling me how is it changing at any point in time. Right? If it's going down, low pressure is coming, right? So this definition, it's the same one that we've got. Now, this notation here, f prime of x, that's the way you say this, f prime of x means derivative. But there's other ways to write derivative. A lot of times you'll say y prime. If the function is y, the derivative is y prime. Another way is dy dx, which you could kind of read like the change in y divided by the change in x, which is the slope. I think they've got others in there. I'm trying to remember the ones that we use all the time. It's like dx, y. That's a little more rare. This is like the really common one right there. dy dx or f prime of x. But even y prime is commonly used. That's not unusual at all. What else was I going to say about that? There's another one which looks like this. And those are not 2's. Those are like curly D's. And this is called a partial derivative. This is called a full derivative. You know, when in the atmosphere, when you take a derivative like this, like if I've got a derivative of pressure, let's say, what it's saying is if you follow a parcel of air, 1 unit of air, as it's flowing through the atmosphere, it's telling you how it's changing, right? If I've got a partial derivative, that means I'm not letting the thing move at all. I'm only letting it stay in one place and taking a derivative. So this is like a full derivative. That's like way beyond anything you'll even do in the first semester of calculus. But partial differential equations are, you know, what you usually end up doing. But where you start with is just derivatives. And that's a derivative. It's something that gives you a formula for the slope for any value of x in a function, linear or nonlinear. Of course, the linear function, it would be a constant slope. So let's see, find the derivative. Find the derivative. We'll do one more like this. Right, the derivative will be, and I'll use their notation, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. So first I've got to do f of x plus h. F of x plus h equals 3 times x plus h squared minus 2 times x plus h. Right? Simplify, right? This is going to be a FOIL. 3 times x squared plus 2xh plus h squared minus 2x minus 2h. So I distributed the minus already. Still got another step to simplify that. But that's one place that you're going to make a mistake. Because we always do. When you've got a minus in front of that whole term, it's going to change both of those to minuses. You got to be careful about that. Because, you know, what happens is, right, you go 3x squared plus 6xh plus 3h squared minus 2x minus 2h, right? You know, if it's a minus, it's wrong. Sometimes we don't have a constant in there, but you can get the constant wrong when now they're adding together when they should be canceling. So now, where's our f of x? Our f of x is this, 3x squared minus 2x. Now notice in what I simplified, those are the only two terms that I generated that didn't have an h in it. Right? Like I said, that's always the case. Zach, you awake? Wow, tricked me. F of x plus h minus f of x equals, cancel, 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 cancel. 6xh plus 3h squared minus 2h. Divide by h. Divide by h. So out of every term in the numerator, we cancel an h. 6x plus 3h minus 2. So f prime of x equals 6, the limit as h approaches 0 of 6x plus 3h minus 2. Direct substitution. What do you get? 6x minus 2. So that equation will tell you the slope of the line for any value of x, right? If you want to know the slope at x equals 2, plug in 2. You want x equals 4, plug in 4. It's a formula. That's what the derivative is. You know, if you remember when we did max and min of even a parabola, but any kind of polynomial, right? If you want to know the max and the min values, that'd be this point there and this point there. You know, what would the slope of a tangent line be at the point that's in between where it's increasing and decreasing? What would be the slope of that line? What would be the slope of that line? What is the slope of a horizontal line? 0, right? So generally, you spend most of the time with derivatives, finding the derivative, setting it equal to 0, and then solving for x. That's telling you where you get your maximum and your min points. Right? when they asked us that question before, we didn't really have a way to find it. Unless it was a parabola. We know how to find a vertex of a parabola. But we didn't have any methods to find it if it was more than a quadratic. But now we do. Find the derivative, set it equal to 0, solve for x. And you'll know exactly what those points are. Okay, now let's look at a square root function, the most basic square root function. Right, so it says find the slopes of the graph of f at these 2 points. Well, it says find f prime of x for this, and then find the slopes of the graph at those 2 points. So we're finding the derivative, same old formula, but let's see what happens with this. Right, the f prime of x, I think I'm going to do it up here. The f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. Right? That's always the same. You know, if it's me, I write it down before I start messing with it. Now let's see what happens when we start to do this, right? So f of x plus h, what is it? The square root of x plus h. Okay, minus f of x. Subtract, right? F of x plus h minus f of x. There's no combining or simplifying or anything we can do here, right? We have this x plus h. Oh, sorry, I'm getting confused here. Minus x over h. Okay, well, that's why we had to learn the rationalizing technique. Right? This thing, if I tried to find the limit of this right now, I would be 0 over 0, indeterminate sum. So how can I simplify that? Rationalizing technique. What would I multiply by if I was doing rationalizing technique? The conjugate of the numerator, right? That's going to be the square root of x plus h plus the square root of x divided by the square root of x plus h plus the square root of x. Still on the screen. Okay, FOIL in the numerator, but again, we don't need the middle term. So it's actually the first term times the first term, x plus h. The last term times the last term, minus x. Right? And in the, I think I'm going to now just h times the square root of x plus h plus the square root of x. Now notice again, in the numerator, you get cancellation. Right? The x's cancel. And then h divided by h cancels. What's left in the numerator when I cancel the h? 1. Right? Don't say 0. So that's what it all simplifies as. Now I can go back up here and do this equals the limit as h approaches 0 of 1 divided by the square root of x plus h plus the square root of x. That's good. Okay, now what do I get if I do direct substitution? Yeah, in the denominator, if the h is 0, right? If the h is 0 here, then it's the square root of x plus the square root of x. So this whole thing is 1 over 2 times the square root of x. Right, that's f prime of x. Okay, now how would I find the slope at these 2 points? Plug x in, right? Remember, the y doesn't matter. Not for this, right? So we're going to say f of f prime of 1 equals 1 over 2 times the square root of 1, which is 1/2. F prime at 4 equals 1 over 2 times the square root of 4, which is 1/4. Okay, before I do that, now the truth is, when you get to this in calculus, you're not going to be doing this process all the time. Okay, that's what's behind the derivative, and you clearly will start the class doing this kind of stuff. I mean, you're going to do a lot of things with limits. You'll find derivatives by doing all this process. But then when it comes right down to it, we have techniques for it which don't involve every time having to go all the way back to a limit. For example, right? Let me go to the ones that we already did. Let's say this one right here, 3x squared minus 2x. Right. For any polynomial term, the way you find the derivative is you take the exponent and you multiply it times the coefficient, right? That would be 6. And then you reduce the power by 1, 6x, right? Same thing here, right? If this is an exponent of 1, I'm going to take the 1, I'll multiply times the 2, so it'll give me minus 2, times x to the 1 less power. X to the 0 is 1. So this is what we found when we did that whole process, 6x minus 2. I mean, you do these kinds of problems by inspection. I mean, there's not really much work to show. I mean, that's all you're doing to find the derivative of a polynomial function, right? You go term to term. Remember how you could take the limit of a sum is the sum of the limits. Okay, well then the derivative of a sum is the sum of the derivatives. Just take it term by term. F prime of x. If f of x equals the sine of x, right? F prime of x is the cosine of x, which means for every point on the graph of the sine, if you want to know what the slope is, just evaluate the cosine. If a function is ln of x, the natural logarithm, the derivative is 1 over x. Now, why would a logarithm and that be related like that? I don't know. I mean, I think that's the kind of thing that gets to, why do we call e the base of the natural logarithm? Because it occurs in ways that you just don't expect. All of a sudden there'll be an e or an ln or something that occurs. And the same thing, look at this function. F of x equals e to the x. F prime of x equals e to the x. It's the only function which is its own derivative. The slope of the graph of e to the x is whatever the value of the function is at that point. So you're going to do the stuff we're doing in class today at the beginning. Everybody does. We used to do more. We used to do a lot more hardcore, like proving of stuff and things like that. But you're going to, at very least, you'll do all the stuff we just did with limits when you start calculus. And, after you get to that, when you get into this stuff, you're probably going to say, well, this is easy. This is easier than pre-cal ever was. That's usually what people think. Okay. So that was the tangent line problem. Again, we use the tangent line problem to motivate why is it we're doing this thing called limits. Because we can't find the limit of the slope of the secant line to use as an approximation for the slope of the graph. And slopes of graphs are important. Rate of change, right? You physics people ought to know that, right? Okay. So the homework is here. Why does it say 9? You can see I was typing this stuff fast. It's not 9 through 11. It's 9. It's just 9, 11, 18, 19, 21, 29, 31. And actually, that's not right either. Golly, I was going fast. This is 17. So next class, we'll take a quiz over the first two sections. Not the one we just covered, right? But the ones that we went over the homework in the middle of the class. Okay. So I'm going to write that down. I need to stop.